All right, so we're gonna go over an introduction over the whole thing quickly, and then laboratory procedure, and then Trayton will take off on the loading variations and the shear moment diagrams, and then Justin will take over for the data calculations and results, summary and discussion, and then let's see, Peter's gonna finish off with the conclusion. All right, so why shear matters? Shear forces are critical in structural components such as beams, bridges, and vehicle frames, as well as many other things, but those are some of the most common ones. Incorrect shear predictions can lead to structural failure, which our whole job as engineers is to avoid. Understanding shear behavior allows engineers to design safe and more efficient structures, generally cheaper, while staying within that safety margin that we're trying to hit. So, introduction to the theory. Shear forces, which we label as V, or let's see, I don't know, there's a Greek letter for it. Can't remember the name of it, but it's the sum of vertical forces acting on one side of a cut in a beam or another structural component that's static. Shear stress, tau, differs from shear force because it accounts for cross-sectional area. So hence why it's a stress and not a force. Um, and shear force varies depending on the load, magnitude, and position. So here's an example of how it varies depending on magnitude and position. So we have W, a distributed weighted load that's distributed over that distance. And then we have a force that's concentrated. And so that's going to change how the diagram, the shear diagram below it in green is going to look. So as you can see, the shear and moments change, and they change, and they're higher in magnitude right around where the structural components are supported, and then they also change, and they're higher in magnitude right around where the forces lie. So um, yeah, and they're related, closely related, shear and moment. We'll get into moment, I think in the next lab, but so let's see, equipment setup. So we started off with the STR3 unit to test frame using four threaded thumb bolts. We plugged in the mini DIN lead from force input 1 on display to force output on the beam support so that it can measure it. We connected the digital force display to output socket, and then from there we powered on, zeroed off the meter, followed the lab instructions that we were given, verified that the small load that we applied was accurate in the display, where it reads off the force. And then if the meter showed a small offset, we tapped the frame a little bit so that it was accurate. And then the procedure went pretty straightforward. The apparatus was secured. We already covered that. It was calibrated to 0. Loads were applied incrementally at specific positions that were in the lab handout, and with different weights. So along the beam, shear forces at the cut were recorded, and theoretical values were calculated after the lab was done.
All right, so moving on to the data and the calculations, um, we were doing experiment two, and this experiment tested three different loading variations throughout the beam. So this first diagram shows the first loading variation. We loaded a mass or a weight on the far left of the beam, and there are two different reaction supports on the top of the beam. So The first, I think on the left one is a rolling pivot, and then the right is a support pivot. And then next slide. So this first diagram shows um, basically the weight on the left equals to 0.98 newtons. And yeah, so that basically will um, change how the shear looks on the graph at the cut. So the cut is kind of in the middle, and then if you um, go directly down from the cut, that shear is exactly what the shear would be at the cut. And the calculations on the side basically just means, or we're basically just taking the sum of the moments about the rolling pivot at A, and then finding the reactions at A and B. And then, of course, the sum of the forces at Y in the Y to find the RA. And then next slide. So this is basically the same thing. I think we had like six different weights hanging on the left, but I just did two diagrams here just to show as examples. But yeah, this one is a weight of 1.96 newtons, and then we got a shear force at the cut of 0.72 newtons if we go directly from the cut. So this is the second loading variation of the beam. So this one we have two different weights hanging in the middle. So this is called the middle loading. So basically we had one weight of 1.96 newtons and then the second weight of 3.92 newtons. And the shear diagram does look a bit different. So again, we solve for the moments about A and the sum of the forces to find the reactions. And that kind of changed the diagram a bit. So again, what we're focusing on is just at the point of the cut. So if we go from the cut all the way down, that should be the shear force at the cut, which is at about negative 3.82 newtons. And then this last loading variation, the third one, we have a split loading. So we have one weight on the left side of the cut and then another weight on the right side. So yeah, this kind of similar to the other one, but it's just split between the cut. So the first weight is 4.91 newtons on the left side of the cut, and then the second weight is 3.92 newtons on the right side. So it does kind of look similar to the last diagram, except there is just a difference in, um, I guess like the cut near the cut is just different. So the shear force at the cut is 2.3 newtons.
Okay, so here are the data that we collected during the lab. You can see we have the 4.4 figure was referring to the left loading examples. We did five of those with five different loading weights, each 0.14 meters away from support A on the left side, and gradually increasing in weight. And we got our reading from the screen, which only had one decimal place to accuracy. And all of the numbers for the first six came up negative and was increasing as we increased the load. Um, and although different in sign conventions, they were relatively or very accurate to our theoretical and calculated values that Trayton just showed us how we got those. As we switched the diagram, or as we switched the weight to the middle and the split load, we actually calculated negative values, which differed from the reading, which were positive values, but they still were very accurate to what we expected. And the equations that we used were just that, yeah, we took the change in the forces in the y direction at that cut, which showed us what the shear force was going to be. And we already talked about what the variables were. But yeah, next slide. And these were the plotted graphs. As you can see, the first one shows how they look opposite from the experimental versus the theoretical. And that's just because the sign conventions were different. But when flipped, you can see how accurate and close every value is. Um, and the sign conventions, we'll get into why there was a possible difference. But basically, it's just due to what we decided was positive and negative is different from the machine. And then looking at how it changes, not just due to the magnitude of the load, using our theoretical, or go back. Um, I used the equation that I made an equation to figure out the shear force at a certain or at the cut, relating to both the weight and the distance that you change. Um, it's the VC equals W times X over L, X being the distance from the support A, and then L being the total span of the bar. And so the first table shows as you increase the distance from support A to the right, you increase the shear force as well. It's not just the magnitude, but it's also the distance. And it's linear as well as the magnitude being linear. They're both a linear relationship. And so when we put a load of 10 newtons, we can find that at 180 millimeters from the support A, it would be about 4.74 newtons, which differs from it being at 0 or at like 0.1, which would be at 2.63 newtons. And yeah, next slide.
All right. So, summary, we found that shear force at a cut is equal to the sum of vertical forces on one side. The experimental and theoretical values agree, and there is a linear relationship seen for increasing point load. So for the shear and moment diagrams, shear is consistent between loads. Where shear is constant, bending moment varies linearly, and shear changes abruptly at loads and supports. An important note is shear is not based on only total load. It depends on where the load are applied relative to the cut. Summary continued. Some of the takeaways. Shear force depends on both load, magnitude, and position. Shear diagrams accurately represent internal beam behavior, and understanding shear is essential for structural design. So getting into that, some sources of error, measurement uncertainty. Okay, so the digital force display could have been incorrect. There's slight misalignments of beam or supports, friction apparatus, and also human error during load placement. In conclusion, the results of this experiment confirm that theoretical predictions of shear force behavior in beams using equilibrium principles. Experimental values showed strong agreement with calculated values, validating the accuracy of statics-based analysis. The relationship between shear force, load magnitude, and load position was clearly demonstrated. In particular, shear force increased linearly with increasing load and varied significantly depending on where the load was applied along the beam. Shear moment diagrams were shown to be effective tools for predicting internal forces within structural members. These diagrams provide engineers with a clear method for analyzing how loads are transferred through a system. From an engineering perspective, understanding shear behavior is essential for the safe design of structures such as bridges, building frameworks, and mechanical components. Accurate shear analysis helps prevent structural failure and ensures that materials are used efficiently. Future improvements to this experiment could include using more precise measurement equipment, ensuring improved alignment on the beam, and increasing the number of data points collected to enhance accuracy and reliability. Overall, this experiment demonstrated that internal shear forces can be accurately predicted and analyzed using fundamental principles of statics. reinforcing their importance in real-world engineering applications. And your references and then the data attachments.
Thank you, everybody.